All right, fantastic. So I'm going to start sort of today's lecture with a bit of general stuff because I feel like there's a general principle here which is really, really useful to know, even if you sort of don't just do representation theory. So this general principle is basically called the block, and I'll give some motivation. So say you've given an abelian category. Say you're working in a situation with an abelian category. If you don't know what this is, consider a category of modules, or a category of representations, or a category of like genes of abelian groups. So like, you know, something where you can add morphisms and take kernels and co-kernels. So call it A. Then we want to like break up A into smaller pieces which don't interact. Okay, so what this means is we say A contains the union of these smaller categories AI. And I mean, I think there are a few different definitions of this. So I'm sort of giving the philosophical definition rather than a precise one, because a precise one may not match a precise one you see in another context. But the idea is basically you want to break up your category into chunks which don't interact in a nice way. So these things such that, so there are no morphisms or short exact sequences between objects in AI and AJ for I not equal to J. Oh, and I should say these AI are full subcategories.
And maybe non-trivial coordinates.
Yes, or
non-split.
Non-split. Yeah. Split.
What does that mean though between the short exact sequence? You mean there's the first object is like A, B, C, where A is in AI and C is okay.
Yeah. Yeah. Like I want to say no X, but simple to just so this. Does anyone else have any other questions about this first condition? It's like there's no morphisms between objects in these separate categories. And if you find something that has a kernel in one and a quotient in the other, it's just a direct sum. That's what this. There's no non-split short exact sequences. They're all just direct sums if you have something with parts in both. Okay, then each X in A breaks up as so direct sum over I, and you know, in our context, and maybe to make our lives easier, let's pretend there's finitely many of these. Okay, breaks up X is isomorphic to Xi, where Xi is AI. And then finally, so each AI can't be broken up further. So I could say, you know, decomposed in this way. It can't be decomposed in this way. So the idea is, you know, you have any mathematical object. It's very convenient if you can say that it's like, you know, built out of pieces which don't interact with one another. And that's exactly what we're saying here for A in abelian category. So, right, so this is the general principle of like, can you break things up into a direct sum applied to the notion of an abelian category? And you can see, you know, if you could do this, then you could potentially just study these things individually, and that might simplify your life. Okay, does anyone have any questions about this definition?
Let's say I not equal to J.
Sorry. Yes. Yeah. Okay, great. So if you're just given an abelian category, like how do you do this? Sort of where would you look to try and find a decomposition like this? So I'm going to give a general way to do this, and then I'm going to specialize to our case that we're interested in of representations. So the general method is as follows. And I think this is a good general method to keep in mind if you like look at other areas of maths, like representations of other objects, for instance, because it makes some things, for instance, in Lie theory, reasonably transparent. So the general method is find endomorphisms, or let's just say find an endomorphism F of the identity functor on A. All right, so what is this explicitly? You know, F is an identity, is a natural transformation from the identity to the identity. And it's so in particular, we've got these maps for each x from x to x. So you want to think of this as like the endomorphism of x for every x, which is natural with respect to these things, right? If you have a map from x to y, you take this map of x, y, and this diagram commutes. Okay. And in particular, you know, you can compose endomorphisms of anything. So, and because your category is abelian, this gives you a ring. So the ring of endomorphisms of the identity function. Okay, so now,
Chris, could you just, sorry, it's a bit fast. Can you remind me an endomorphism? What it means, an endomorphism of a morphism?
yeah, okay, so this is a good question. So identity of A is a functor from A to itself. And we're interpreting this as a morphism of functors from the identity to the identity. So what does this mean? This is a general like natural transformation between any two functors, has the form for each x in your category. So maybe I'll write a general natural transformation like this is the data of tau x from f of x to g of x, such that it's natural. And so when you unravel what that means when both f and g are the identity, it's saying that you've got a map for each object, goes from x to x, such that for any map of objects, this square commutes. So really, you should think of this as like a canonical way of acting on every object at once in your category. Okay, now, so now if the Hom spaces are finite dimensional, I mean, this is possibly too strong, K vector spaces, as in, like whenever you're doing linear algebra or like linear algebra with extra structure, like principally representations, then Fx has eigenvalues. Well, really, I might say generalized eigenvalues. So this is the idea that, you know, Fx is just a map from x to x. This is going to be a linear map because we're working, you know, in places where we can interpret our morphisms as linear maps. Or, sorry, we can interpret them as endomorphisms of vector spaces. And doing this, we can say, okay, well, you know, by general linear algebra, we always have eigenvalues for a linear map. And this naturality actually tells us, well, maybe I should say, and then a proposition, which isn't too hard to show, if the x, and let's finite dimensional, sorry, K algebraically closed. We always have this, but like we always want K algebraically closed to do this. But this principle is more general. Then x breaks up into the direct sum of x lambda I, where x lambda I is the kernel of f of x minus lambda I identity on x. So possibly some large power again. So generalized eigenspace of type of lambda is the idea.
And a bit. So I don't think. So I think that what you're thinking in your mind is that
We're secretly over vector space.
there were secretly
Yeah.
that our category, we can interpret objects in our category as vector spaces with extra structure,
Yeah,
which is not the same thing as having.
yeah, it's not quite the same thing as having k-linear homosets. Yeah, so maybe I should. Because there was probably a statement of this which works in more generality, but maybe let's say now if let's just say A is finite dimensional vector spaces with structure. So finite dimensional vector space with structure.
So admits a faithful, if you want to be fancy, admits a faithful function
to K vector space.
to
Okay, yeah. So I don't know what I want to say. Well, okay, yeah. A admits a faithful function to vector spaces is one way of phrasing this. Maybe I could just make my life easier and say we're working with representations of something. But yeah, I guess as with all of this, with the sort of nebulous definition, working in a context where we can do this is the important thing, and such contexts arise very frequently. Okay. But yeah, basically the point is, endomorphisms of the identity consider their eigenvalues or generalized eigenvalues on every object. Then this actually breaks each object up into objects of our category, or like sub-objects. And so homs from x lambda I, y lambda j equals 0 if I does not equal j. And short exact sequences split. So this is basically saying, given an endomorphism, we get a decomposition of our category into this just by considering the generalized eigenspaces of that endomorphism on every object all at once. Okay. Does anyone have any questions about this one? Or if you haven't seen it before, that would be good to ask a question.
What?
Like if you haven't seen this stuff before, please ask a question. Yep.
Is there like a nice concrete example?
Yes. Soon we will do this in KG mod. So red yeah. So I mean, because I think the difficulty is like, okay, great, start with an arbitrary category. Like, why would you know this? Like, where do these come from? Okay, so we'll get to that. But the idea is, well, the thing to remember is that endomorphisms of the identity break up objects into generalized eigenspaces. So now,
can I also ask a question?
Yep.
So what I would do for building categories, I would look for a projective generator, take its endomorphism space, get an equivalent category, and break the ring into indecomposable summons. Is that the same?
you are jumping the gun. That will end up being the same, but yes.
Okay,
That
fine.
will
It's good.
But I was hoping that someone would, suggest the more natural way of breaking up a category in this way. Because there's sort of two ways you can do it. Though this one doesn't rely on a projective generator, which is a pro. But okay, so
And just to comment, so
Yep.
I hope it's clear to everyone, but short exact sequences split means, it doesn't mean that all short exact sequences split.
I'll make that precise. Where split of the form, x lambda I lambda j. So it's like if the pieces are in different eigenspaces, then they can't have non-trivial extensions.
And maybe another question is similar to Isaac's question is, what does this mean in terms of good old Jordan canonical form?
Yeah, so that's a good question. So the idea is, what does Jordan canonical form say? One way to say is that every matrix is similar to something in Jordan normal form. And what is Jordan normal form? It says you've got these eigenvalues along the diagonal, and then you've got possibly some ones, and those are your Jordan blocks. So they're indexed by like eigenvalue plus like size, and the size you can do the potent part, the eigenvalue is the eigenvalue. And the point is, for an arbitrary endomorphism of a vector space, you can always decompose into these pieces, and it's always a direct sum. And you don't, the idea is that any map, I'm not saying this very well, like the idea is that any map which commutes with your endomorphism has to preserve those Jordan, the like eigenvalue clumps of Jordan blocks, is the idea. So, right, so you're an endomorphism of a vector space, you're interested in things which commute with it. That thing decomposes your vector space into generalized eigenspaces. That's your Jordan decomposition. Anything that commutes with it has to preserve those generalized eigenspaces. So you sort of, all of your endomorphisms also, act on the Jordan pieces separately. Is there a better way to phrase that? Because I feel like it's very clear in my head, but that example.
That's pretty good to me.
Yeah.
So why don't I just take F to be the identity
Well,
on this board?
when we take F to be the identity, what do we get? Well, the only non-zero eigenvalue is 1.
Mm-hmm.
So every object gets decomposed into a single thing. And so like it
So
gives an
what-
example of this, but
Okay, we're done.
one
We're
which doesn't
done.
help.
Okay, so you want something specific or more specific than that?
Yeah, yeah. You want to break it up into smaller pieces. Yeah, like you can do this for any endomorphism, and also, for instance, zero endomorphism also won't give you a non-trivial splitting.
But the splittings for different endomorphisms compatible with one another.
That is a good question, which I do have to get to. So useful, well, I would say a beautiful lemma is that endomorphisms of the identity functor. This is a ring because we can add morphisms and we can compose them. Is commutative. So if you haven't seen this before, this is kind of like amazing. This is a really amazing result. Think about how difficult non-commutative rings are, and commutative rings are so nice. And this says for an arbitrary, even additive category, this ring is commutative. So it's very, very powerful, even though the proof is not very hard. Proof is sort of write down what this would mean and then say, oh, this follows. But okay, and this story works for all of the endomorphisms at once. All right, so this was exactly your question. What if we have multiple endomorphisms interacting with one another? Well, because this thing is commutative, they will preserve each other's generalized eigenspaces. And so these they may possibly break things up a bit more. But if you look at the whole ring, you actually get a decomposition into generalized eigenspaces for characters of this commutative algebra. So the word character is very, very overloaded in what I'm saying, so I will give the actual definition. So I'm still going to call it a character though, or character of, maybe I'll just say a commutative K algebra is an algebra map A to K. So joking. Right, so, and then when I say that this story works for all of them at once, we get that each X breaks up into direct sum of X lambda, where lambda is a character of endomorphisms of the identity. And so this X lambda, you should think of this as like the simultaneous lambda eigenspace for all of the endomorphisms at once. So I would say this is the kernel of F minus lambda of F identity. The intersection of the kernels of this. Where these are endomorphisms of X. So
you take like power into right? Or
So you need to take that too. And this is where the finite dimensionality assumption comes into my second. We can just let n be suitably large and this will be fine.
what did you take in the intersection?
Yeah, sorry. So this is like taking the intersection. If we're secretly working with finite dimensional vector spaces, this is just a finite intersection. Like if you're because the idea is if you have one endomorphism, say the identity, it may not break your objects up at all. And then if you have another endomorphism which commutes with it, it might break them up a bit more. And another endomorphism, it might break them up a bit more. But if you take all the endomorphisms at once, like it can only be broken up into certain pieces, and there will be finitely many, and they will sort of partition your vector space into generalized eigenspaces. Now they're indexed by capitals. So you want to think of these as like eigenvalues of this whole commutative alpha acting on vector spaces.
So you're claiming that there should be a fixed n that's large enough, or you still have to take a union over all n?
There will, I mean, in the finite dimensional setting, there will be an n which is large enough. So this is the idea that like if you had Jordan blocks,
Of course,
that
yeah.
have bounded.
You're saying if what's finite dimensional, or you're saying if it's
Like, yeah, maybe I'll make this. So A has a faithful functor to vec, where U is faithful. Finite dimensional A vector spaces. So you can imagine everything as vector spaces with a bunch of stuff via this faithful forgetful functor, and that's what breaks up your eigenspace.
So n depends on the dimension of x.
oh, it depends on the dimension of x. Oh, you're not. Oh, sorry. I thought you were giving me a description of the cat. Okay, sorry. I'm sorry.
Yeah, maybe I just
X. Yeah. Thank you.
sorry, I realize
Okay, you're not. You're. Okay, yeah.
trying to keep things a bit more fuzzy, but it may not make things easier.
Yeah. Okay.
Yeah, and maybe I'll say, so this statement goes, the general version of this statement goes by the maybe Ekman-Hilton argument, which is like, I would say one of the most beautiful results in category theory, even though it's completely elementary. It's like, category theory, there's a lot of soft nonsense going on. It's very abstract. You're like, how can this actually help me? Knowing that a ring is commutative is a very, very, very strong thing to know, right? Like that is a really, really strong thing to know, and it's very, very helpful. For instance, this is also why higher homotopy groups are abelian. You know what those are, which is a very deep fact, proved in the exact same way. It's a deep fact with a lot of history. Yeah, and so like the reason this works is that commuting commuting matrices can be upper triangularized simultaneously. Just the fact of linear algebra, which isn't too hard to prove. Okay, so now we're going to sort of quit this abstract stuff and go down to the category we care about, which is KG mod. And what does this look like in this category?
Chris, before you do that, what's the simplest example? Like, can you take A to B vector spaces? What is the n by? Like, is there a simple example?
Yeah, so I would say the simplest example that's non-trivial is probably RevG.
Okay.
So yeah, or okay, take any one way of saying is if you start with a commutative algebra and look at A modules, then any element for A in A acts on any A module, right? By you've got this map for any module which says multiplied by A. And then for this to be natural, you need this square to commute, but this is exactly the statement that F is A linear. But then you might say, okay, well, why did I say that A had to be commutative? And it's because for left multiplication to be a morphism of A modules, you require that your ring is commutative. So that is probably the simplest example. But yeah, I think rep G is a good example because it really sort of gives you the power of this idea. Okay, so now I claim, I'm just going to tell you what this is in rep G. It's isomorphic to the center of the group algebra. Right? So, okay, yeah, so why might this be true? So here is one way to see that this is true. So this thing, these are basically what are the things that you can do to every vector space with a G action that are natural, right? So you have a vector space with a G action, you can multiply by anything, any x in KG, but this won't be G linear unless x commutes with all the elements of G. So only is G linear if x commutes with all G in G, which is to say that x is in the center of KG. Now, the other direction is not difficult, but I don't think I want to say it, but it is a good exercise. Like the general statement is the endomorphisms, the identity functor for modules over any ring are isomorphic to the center of that ring.
Yeah, so one needs to complain a little bit there because, like, I mean, you're assuming finite dimensional the whole time, no?
Yeah.
Yeah, so it's not true that the center of the endomorphisms of the identity functor on finite dimensional modules over a ring is always the same thing as the center of the ring. That's true for finite dimensional algebra.
Sorry, yeah.
You need the regular module to make
Yeah. So you either need your algebra to be finite dimensional or work with the category of all modules.
Yes.
And correct. Yeah, so I would say the general statement is true in the appropriate category, would be one way to say it.
Maybe that's so. Maybe it's worth writing just, you know, for a finite dimensional algebra or something, because that probably gives Alan many examples.
So general fact, and this general fact is proven in the exact same way. A finite dimensional algebra over K, then the endomorphisms of the identity functor on A modules are isomorphic to the center of A, which is a commutative algebra.
So how many pieces do you get?
So how many pieces do you get? Well, that depends on your algebra. But in this case, the case that we're interested in,
For commutative algebra.
for a commutative algebra, it gives you the number, the dimension. Sorry, for a finite dimensional commutative algebra, this gives you the number of simple modules. Okay, so let me say what the upshot of all of this is. So rep KG upshot, rep KG splits into blocks indexed by characters of the center. Of KG. So the idea is this acts on every representation. And because it acts on every representation, for instance, on a simple representation, it will act by scalars, that's Schur's lemma, which means that it will act by a character, in that sense, on any simple representation. Which means that, and then you know that, okay, well, the simple representations with different characters, they're not allowed to interact. So this sort of splits your category up a bit. And for instance, in characteristic 0, every symbol has a different central character. And that, tracks with the fact that in characteristic 0, symbols are not allowed to interact. So if you, took rep G for a finite group in characteristic 0, you applied this recipe, you would sort of find that, okay, everything splits into symbols, we've got the correct number of them, and so on. But it's very different in the modular case. You can have multiple symbols with the same central character. Okay.
But roughly speaking, the bigger the center, the better.
The bigger what?
The bigger the center, the better.
Yeah. Bigger center means more
Space for symbols.
Yeah, more central characters, therefore more splitting into little bits, so each of the little bits ought to be smaller. So having a big center itself.
So this, so you're summing the elements of the conjugacy class
To get the center.
to get elements in the center, and then taking the character is the normal idea of taking a character.
Yeah.
Sort of.
Yeah. So I'll write this in a better way. So, but first I'll give the definition. So I'll write rep kg for the lambda or the lambda block. Okay, where this is just some linear character on the center. But okay, so let's actually understand this a little bit more just in the case of, say, characteristic 0, ref G. Because it's worth understanding this center. So I feel like, so the center of kg has a k basis of CG, which is defined to be the sum over G prime conjugate to G of E G prime. In other words, the conjugacy class sum. Okay? And then if you want to know sort of how this acts on a representation, well, in characteristic 0, say, what we do is in characteristic 0. So characteristic 0 say V is an irrep, then we have the map from AG to NB. And where does our conjugacy class get sent to? Well, V is an irrep, which means by Schur's lemma, any endomorphism of V must be a scalar. Okay, so CG maps to equal MV of CG times the identity. Okay, this doesn't help you yet. I'm just sort of defining what this is. But now I claim that we can actually compute this number in terms of things we understand. So take the trace of CG in NB. Okay, well, what do we get? On one side, we get lambda v CG times the dimension of V, because it's a scalar, right? It's a diagonal matrix, and you're summing up the entries. However, we also could take some, G prime conjugate to G. By definition, this is the character of this, the trace of this element on this representation. But these are all conjugate, so they're all the same, which means we just get the size of the conjugacy class times the character on any G inside that conjugacy class. Right? That means we have useful formula for finding the central characters. This is size of the conjugacy class times the character value divided by the dimension of it. So yeah, so this sort of tells you that central characters in characteristic 0, it's just given from the character table and is almost equivalent to the information of the character table. I would actually say it is equivalent. Right? It's equivalent information to know the central characters or to know the whole character table. Right. Okay, does anyone have any questions about this computation or like the point of this computation?
There's a question.
A really dumb one. What's E sub G? Is that just
Sorry, so E sub G is
inside the group element inside the algebra?
yeah, that's for the basis of the group algebra in respect to elements. Okay. So yeah, so this was one recipe for chopping up KG into a bunch of subcategories in a nice way. And they're indexed by central characters. And you know, in characteristic 0 at least, it's clear what these central characters are. And I'll in a bit we'll hopefully see that we can also build these central characters in characteristic P. So in the modular case we're interested in, one can also deduce this from the character table. Actually, maybe I'll just say that now, in case we don't have time. So the idea is this is a central character, and it turns out, or it's not too hard to show, that this is an algebraic integer. Right? So the reason being is that this thing generates a finitely generated Z module. So a Lemon commutative algebra tells you that any eigenvalue of it will be a algebraic integer. But that's if that didn't speak to you, that's fine. Like take it as a black box, this value is an algebraic integer. And it's important that it's an algebraic integer. For instance, if this was rational, this would be an actual integer. And the point of that is then we can reduce it mod P. So you know, if we have an algebra homomorphism to algebraic integers, we can just compose with the map that reduces mod P, and we get a mod P algebra homomorphism. So the point of this is that like from this character theoretic, there's character table in characteristic 0 data, one gets algebra homomorphisms in mod P. And that gives you a decomposition into blocks of your category, and it's very useful. Okay, but I'll say a bit more about that in a bit, but I want to now go back to Daniel's comment, which was, okay, like if I had a category of modules, shouldn't I just try and split up the algebra instead? Like, so one way of building pieces of a category which don't interact with one another is the following fact. If A, an algebra, is isomorphic to A1 cross A2, then A mod sort of breaks up into morally A1 modules and A2 mod. Okay. So what do I mean by this? Like there is a central idempotent in here, and there's a central idempotent in here, and you can hit any module with those idempotents, and that splits any module into 2 pieces. And so the subcategories are like the things which are fixed by certain central idempotents in your algebra. So let's go back to KG, because this is the sort of familiar world. So KG, this is a sort of new definition. You can say B blocks EB AG EB, where EB are primitive central idempotents in this algebra. In KG. Okay, so this is the general fact of, take any algebra, break it up into sub-algebras. You can always sort of, well, in finite dimension, you can always just do this, break it up into a finite number of pieces that can't be broken up any further. Then your idempotents are called primitive, they can't be broken up further. And the fact that this is a direct sum gives you that these idempotents are central. Okay?
So in order to be a pain in the neck, so this is typically what happens at finite group thing. People say, in what category does that decomposition occur?
In what category does this decomposition occur?
Yeah.
For me, this occurs in the category of K algebras.
I think that's
Where, well, I'm using direct sum
in a very
potentially,
weird way.
yeah, maybe I should say product. Yeah, it's like, it's the product of algebras, but I often see that written as direct sum. It's just like component wise information.
Or maybe it's something like when if you take a product of what, so what's the one? So the unit is the product of the units, yeah?
The unit here maps to EB1, EB2, EB3. So yeah, so I guess these are, it's the product in the category of it is the product. So then I guess these are non-unital algebras would be the problem. Or sorry, no, these are unital algebras, but the map from here to here is a non-unital algebra.
Yeah.
That is the yeah, which is the correct way to say it.
Okay, so what category are you taking?
I mean,
What's the final answer?
okay, yeah. So the final answer is that like this is an algebra, or you could even think this is a ring. Maybe I'll make it very clear. Splits as a product of subrings. Like you basically can think of this as components which belong in each of these. Multiplication is done component-wise, and each of these is a small algebra. Yeah. I mean, yep.
Sorry, so what's the takeaway? The problem is the identity in each of those subring, i.e. the blocks, is not mapping to the identity, it's mapping to a primitive idempotent.
Yes.
And so it's just, what is your definition of a ring homomorphism? You're losing the property that the identity has to map to the identity, and that's why it's not in rings. Is that like the subtlety that Jordy was concerned about?
I don't think, well,
Yeah.
I don't necessarily think so, because this is true as a categorical product. So in the category of K algebras, this holds true on the nose of unital K algebras with K algebra homomorphisms. The only thing which doesn't hold is that in the category of K algebras with unital homomorphisms, you do not have morphisms from here back into here. But you don't expect morphisms from the components of a product to go back into the product. So that's something you expect with direct sums. And to get it, but you do want to sort of be able to do that. So you say non-unital stuff, and often people write direct sum because it's all linear. As a vector space is the direct sum. Yeah. Okay. So the most important thing with this is that like these two definitions, I've said, blocks as primitive or sort of subalgebras which can't be broken down anymore. These two things are equivalent. So these two definitions, these two ways of breaking up your category are the same. Position is two ways of decomposing rep KG are the same. Okay.
I mean, to be another pain in the neck, you didn't actually say how that gives a decomposition. Oh, so you're saying if I have such a product, then blah.
Yeah, so I guess it would be this remark, but the actual thing is that we could say rep A V G equals those V such that when you act by EV on V, you get V itself. So this is the decomposition into chunks of rep. Okay. So
Does everyone know what a primitive or central idempotent is?
No, okay, so, yeah, so the idea is like, the general fact is given a ring and an idempotent in the center. So this is an element which squares to itself, that gives you a decomposition as a product of two smaller rings. This works for non-commutative rings as well, but you need to make sure your idempotent sits in the center. When you do this, you can break down your ring into a product, and then maybe break down that into products and products and products. If you can't break a ring down into things anymore, the idempotent which gives you that summand is called primitive. So yeah, this is like the strategy of trying to decompose your thing into parts which don't interact, this time applied to a ring. Like we saw it applied to a category with blocks. This is, you apply this to a ring or an algebra, you get a decomposition, and we see that taking like module categories, these two notions agree with one another. Yep.
So if you have one of these E's, what's the character from the center on the center? Or is that?
That's a good
not
question.
obvious?
It's not obvious. Well, like at the moment, it's not obvious that these two things are sort of the same, because I've given you two ways of decomposing. Saying that these are the same is to say that like like each piece here has a central character, and only one central character, and every central character corresponds to one of these pieces. This isn't super obvious. Yeah, and so in the interest of time, I'm wondering whether it would be better to explain why these two things are the same, or to give an example of computing some central characters mod P.
I'm in favor of an example.
You're in favor of an example, yeah.
But is the word orthogonal missing here?
I guess if you can do this, they will be orthogonal. But
Oh,
I think you're.
Oh, I see.
Yeah, I think to be safe, you could say orthogonal, but like then you could say, a maximal set of primitive central
Yeah, okay.
orthogonal.
No, it's fine.
Yeah. I don't know. There's a lot of adjectives for something which is easier than it looks. It's like splitting a ring up into bits. That's really all there is to it. I learned that in Algebra 1, but I don't know if that's standard Algebra 1, but like, I feel like that's okay. Okay, so let's look at an example. But first I want to, use this idea. Sorry, yeah. Before we look at an example, one more thing which needs to be said, which is that all of this block stuff, over characteristic 0, I said that everything is semi-simple. So when you do this recipe, you just get a bunch of things with a single simple in them. You have very boring individual categories. You do this mod P, you get much more interesting categories. You can have multiple simples tied together in the same block. But there is a way to go from characteristic 0 to characteristic P.
So the idempotents in this case are the ones you wrote down last time, right? Oh, did you write them last time or just in our discussion?
I think just in our discussion.
Okay.
I think because in general it's easy to write them down in characteristic 0, but we primarily want.
Right. Okay. No, fine.
Yeah. But okay. So the important thing is, we know that the central idempotents of maybe I'll just say the idempotents of the center of KG correspond 1-to-1 with the idempotents of the center of AG. Remember, A is this like integral interpolating ring between characteristic P and characteristic 0. And so this is the idempotent lifting, or the like lifting of projectives, because projectives are like tied to idempotents. So this is the idea that idempotent stuff can be lifted to characteristic 0 by this one ring. But this ring has a very natural map to the center of KG in characteristic 0. Okay, so the upshot of all of this is that for some linear character of the center in characteristic 0, which maps to K, we can pull it back to a linear character of the center of this thing, and we know by this correspondence that it corresponds to an idempotent of this ring. Okay, so it's not, yeah, so say given lambda, we can pull it back, get some lambda tilde, and then lambda tilde corresponds to, well, even better, I will say that because this has characteristic P, we can factor this through a set of kg, and this gives us our lambda hash.
We do the character of the kg in the middle.
Yeah. So if we had a character, because remember this is oh sorry. You're right, yeah, absolutely. I should either draw this diagram bigger or
You want to write your integer?
yeah. So we could pull back a character to get something here. But now this corresponds to an idempotent in here, and then via our idempotent lifting story gives us an idempotent in characteristic here. So sort of what is the point of all of this? The point is that we can say, take a representation, a simple representation, characteristic 0, reduce it mod P, you know, you pick a lattice and reduce that lattice mod P. If the center acts via a scalar before you reduce, it will still act via a scalar after you reduce. And therefore, that gives you like a central character mod P associated to each irrep in characteristic 0. Okay, so yeah, so in the interest of time, I will say the upshot, the huge upshot. Like, if there's one thing to remember from all of this block stuff, it's that this gives a characteristic P central character for each characteristic 0 central character. You know, via reduction mod P. So this story of pulling back is equivalent to the story of reducing character values mod P. But the important thing is that you can do this. So partitions the irreps in characteristic 0 according to the blocks to the blocks in characteristic D. Okay, so yeah, this is sort of the point of this whole first lecture. So maybe I'll just talk about this further in the second one, given that it's 5 o'clock. Yeah, maybe I'll talk more about this in the second lecture, because this is really, really important and worth emphasizing to a massive degree. So does anyone have any questions about this? I'm going to talk more about it.
Right, so the point here is that some of the characters can now collapse and are now the same in characteristic P.
Yes. Yeah.
So you get a coarser decomposition, I guess.
Yes. Yeah. And so it's like you don't expect symbols to reduce to symbols. And in characteristic 0, so the symbols correspond to central characters. But when you reduce these central characters, you get multiple central characters agreeing, and then all of those symbols live in the same form.
Right.
Okay, well, how about we have a 5-minute break?
Your organal already linked. Because of centrality. That's the development.
So it's automatic for your phone. Right, so if you don't have central ones, I would need orthogonal because on the isotopic components they can be created in that.
Yeah, I guess if you put the word orthogonal here, you wouldn't need the word central.
But
because it's in
but it would be illegal
How's it going?
because illegal.
like there would be more of
They're more orthogonal ones, right?
Yeah.
Oh, I guess if you had a primitive orthogonal idempotent such that this held as a decomposition into alpha, then they would turn out to be something. Yeah. And so like,
Yeah, that sounds great.
You haven't done any modification yet.
yeah, I feel like I definitely sort of because this idempotence in rings is like one thing that I remember very distinctly learning. So I feel like to me it's really, really like intuitive, but I realize now it maybe isn't taught in every like algebra one. So yeah, I definitely feel like I could have. I don't know. Yeah, so the idea is if you have a decomposition like this in the central items, the claim is that any EB times EB prime gives you 0. And the reason that is because, well, decomposition to this is a product. So EB sits in one.
When would you like it?
Another factor of the product, you multiply them, and they're the same return. Bye.
Like the so like every object is fine, like, and I think you can find. Because then you're equivalent. Pop others are thinking to find which one is like, well, nice, hold on. Find which one it does have.
Yeah, that's right.
Everything is fine. So much this.
As in finite implies that
Wait, so every.
Like, you see that we're trying to do
Come on. I mentioned a while ago.
Yeah.
He's going back. As in negotiation. If you're not fighting,
I get this still like time.
Sorry?
It's
It's on.
Oh, yeah.
You don't want to. You don't want to threat the recorder. I turned it off as soon as the second time. If you want to ask the secret question. But it's still on, yeah.
That's.
yeah, but I mean, I've never understand it. Which is never oh, it's like it's a place that you can.
Right, it's not a statement.
Yeah.
Okay.
Yeah.
So there are many different things about it. So it's like you actually everything we were. Just trying to get all right. There is trying to survive.
But it's all right. I mean, yeah. It's fine. But yeah, I can get good things to it.
Terrible block. Right next to it.
You're doing a real good job.
No, but I think it's cool. People know like there's
So then.
like it has frictions.
I answered to your
That's like a negative 5.
Yeah, ask you.
Something that everything inside is like
I suspect you and
it's 25. So it's like everything
What
inside
is
is great. You want to think of the equation as kind of like
so
with the code.
yes, so it depends on
the definition is basically things that haven't filtrated
but if you're in
explosions.
it is so like A1 is just
And then with that definition, if there is, and I want to say that it's something corresponds to a gradient of sorts. And I think there is a categorical trick where you just like move it, but it's like makes your rings massive and makes it very opaque. You can secretly think of this like rotation length as an it would be but like sort of not really this way. Because I feel like it's a really useful mental trick to be like, oh, I'm doing the filtered objects everywhere. It is given exactly by the Yeah, I mean,
usually you can't think of it.
no, you can't think of those. It's great. But the idea is like, if you take the associated range object when you build it up, you get something. How do you remember sort of what you had to begin with? The claim is that you have like, with odds, you're really so like this massive. There was the result, but obviously it's so basically, I don't know, this is. Yeah, I wanna do start with, I think it's like, well, and then we see. I think, things out of so this. That was one. Maybe say that I mean, yeah, I think that would be a great, that would be a great excuse. I mean, I've always used language for towns. People was like, kind of my main, the you start school. Yeah. Yeah, and because it is like, that's right, I just into the like, I have an interview in the category. Yeah.
I've just seen, there's like that one area where it's like mixed pouch mushrooms with a young man. You got this paper. So it is.
But it's like,
People love like
having you can just write a little line, give it to that version, I don't want to be something one day.
There's a good person.
And then I'm sure someone will be like, I don't like this button from one.
Maybe you should restart.
Oh, yeah, it's just been totally unsurprising. But, all right, so if I can, if I'm gonna need to move this,
Beautiful day. Oh no, I'm good, the camera didn't catch it.
I was.
Oh, you're just saying, that's right. That's fine. That's right. You gotta write it in like 3 days. Oh,
right, so I thought it'd be good to do an example of this, so. Let's look at S4 and characteristic 2. So, we'll recall this formula for central characters in characteristic 0. Okay, so first, let's draw the character table of S4. Yeah, I think I'm ready to do that.
Chris, it's very good training just to practice the right figure.
But it's not important what these are.
Yeah, I know, but just like whenever you're giving lectures, like just try to write figure and you ever think that you're gonna need it.
All right. So I need to fit 2 of these on the board, so I'll try and
like use multiple boards, that's fine.
All right.
Make it readable for people with bad eyesight like me.
Should be. Yeah. All right. So I'm gonna fill in this character table. Hopefully this is familiar by now. 1, 1, 1, 1, 1, 1, minus 1, 1, minus 1, 0, minus 1, 2, 0, 3, 1, minus 1. Okay, so this is the character table for S4. Now we're going to do by hand, because why not? Compute the table of central characters. And so I'm just going to be applying this transformation and keeping things in the same place, because you really can't do this by hand. And the point is, we don't reduce these entries mod p, we reduce these integers mod p. So this is 1, 6, 8, 3, 6. 6, 8, 3, minus 6. These all going to be 1s. Okay, great. So this is the central characters of S4 in characteristic zero. And so here are our conjugacy classes. These are our irreps. Maybe for completeness, I'll write them down. Trivial, sign, two-dimensional thing, three-dimensional thing, three-dimensional thing, twisted by the sign representation. Okay, so the point is we can determine the blocks in characteristic 2 or characteristic 3 by reducing the entries of this mod 2 or 3. Okay, so let's just like reduce mod 2 and see when things are good. Okay, so reduce mod 2, these are all even, so they all go to 0. These are all even, goes to 0. These are all odd, they go to 1. These are all even, goes to 0. So we see that all of these reduce mod 2 to the same thing. All right, so that tells us that for p equals 2, there is a unique block. Okay, so p equals 2, unique block. And some terminology, which maybe I'll write down on the other board, but the principal character has a block associated to it, which is called the principal block.
Trivial character.
Trivial character, sorry. Trivial character has the principal block associated to it. And so in this one, we could say at p equals 2, the principal block is the whole thing.
Chris?
Yeah.
You go through the reasoning again, so you reduced everything. You got a multiple of a single thing. The result. What's the reason why there's a unique block?
So that tells us that all of these central characters, when you reduce them onto the same central character, and then it's a corollary of array is that all of the central characters mod p show up by reducing characteristic 0 ones. Okay, now what happens if we reduce mod 3? Okay, so we see that mod 2 just got one big block, category doesn't break. Mod 3, well, immediately we see that this and this are not the same, mod 3. So we see that mod 3, this thing, and this thing are a single block. So these 3 central characters or these 3 irreps all belong to the principal block. And then you've got these 2 things, which are both different. Okay, so our blocks are B and single. And this partitions our characteristic 0 simples into blocks and also tells us that mod 3, we're going to have 3 separate chunks. Now, we can relate this to something we saw last week. To see these simples, 3 divides them, and 3 is the largest power of 3 that divides 24. Okay? Which means that when we reduce this, we get a simple and a projective module. Right? That was sort of the corollary of what we were talking about last week. If the dimension of this guy has lots of powers of p, has enough powers of p, then it reduces to a simple, which is also projective. And think if you have a simple module that's also projective in repkg, it actually doesn't have any maps or extensions to other things. So like you can think of that as a block. Like, well, it is a block. The things which are sums of that single simple projective form a block. Okay. And here is another one, and we see that these 2 are distinct. So in the sense that we found a simple and a projective by reducing this, we found a simple and a projective by reducing this. We actually found the simple and the projective, we found the simples which live in these 2 blocks of the category. The mod 3 representation. And so then, what lives here, well, you'd have to reduce these 3 to see what you get, to get things which live here. So this is a nice way in which your life can sort of be easier by restricting attention to just a block at a time. Now, okay.
Can you explain how you got those blocks again? I'm confused.
Sure, yeah, so.
You're working on 3.
Yeah, so basically reduce these entries mod 3. That gives you the central characters mod 3. We see that there are 3 of them. So therefore there are,
So how do you see that?
oh, how do we see
Why
them?
do you get 3 blocks?
Because these 3 reduce to the same thing. And then this reduces to something different, and this reduces to something different. So like,
This is last 2 reduced to something different. With the same thing.
The -2 at the end.
Oh,
there's
There's a
yes,
minus
and
two.
also yes, up there. Yes, there's -2 and there's -2.
thanks.
Right.
Can I just say something that's like I don't know, my mental image of what happens is like, I don't know if people have seen in algebraic geometry, but there's a very common situation in algebraic geometry where you have a family of varieties and they're very nice, and then at some points they develop some crazy singularities. Yeah. And what happens is you can imagine the category of representations of a group as somehow similar. So at a generic point, like over Q, like let's say that we're symmetric groups or something, so there's no rationality questions. At a generic point, you just have these matrix rings. And matrix rings, you should think, are non-commutative smooth things. So they're very beautiful, smooth things. And then as you go to these primes, some of these matrix rings kind of coalesce in very complicated ways. But they coalesce into kind of different blocks, and well, different blocks in an informal sense, which are the blocks in the formal. Yeah. And so in this particular case on the left, when you take this thing and you look over the prime 2, everything sticks together and forms this like really crazy complicated algebra. And over the prime 3, some stuff sticks together, and then you have these 2 dudes that are off by themselves.
Yeah, that's a really nice way of thinking about it. And I think one other thing which is worth pointing out is that these, like this case here, when you've got your simple, which is projective, which is in its own block, that corresponds to when this algebra is matrices. So like these algebras are very complicated. Simplest non-commutative algebras are matrices, and that exactly corresponds to when your simple is also projective.
And also the central idempotent reduces nicely mod P.
Yes. Oh, yes. So
Okay, can I ask you a question before?
Oh, sure.
For me, the principal block is kind of always the most complicated.
Yep.
So in your process, is it true that most simples will end up in the principal block? Or is it just a coincidence here?
I mean, I think that's true, but I don't. That sounds dangerously similar to statements which could be very, very difficult and
I agree. That's why I'm asking.
Yeah, like does the principal block always have the most simpleton?
But for intuition, it's good. I think it's
Yeah,
good
yeah.
intuition, but no idea if it's true.
Okay.
Yeah. Is that a formal conjecture that the principal block has the most simples?
No idea.
Is it true that the principal block of simples have dimension which is co-prime to P? Like it's non-zero, in other words?
No.
Oh, so you can have.
Yeah, and in fact, I may as well state this conjecture now, because it's really cool. The statement that if all of the things in a block have the same powers of P dividing it. Okay, so in this case, this is co-prime to 3, this is co-prime to 3, this is co-prime to 3. That's called a height 0 block. And the conjecture is that, for instance, maybe I'll just say it for the principal block, if the principal block has all of these things co-prime to P, then that implies that your silo P subgroup is abelian. And that's a big conjecture that was proven last year. It was conjectured by Brouwer like 6 years ago or something.
Isn't it the other way around? The height zeros are the easy ones and the high heights are the difficult ones?
No, high powers of P are easy. So saying that all of the things in your principal block are co-prime to P.
I'm confused about the terminology. Sometimes you read backwards. Like the ones that are co-prime are very high power, named of height 1, I guess, in this case, because the maximal power would be 1. So you kind of read backwards.
So height is so low defect means high power of P.
Oh, it's the defect. Sorry.
Okay.
Sorry.
Low height means low power of P.
Yeah, no, sorry.
Sorry.
I confused height and defect.
Yeah, no, and height is actually more about how the heights of things in a block compare to one another. Is how yeah. So like that's an incredibly deep set, which was only proved last year, and it's a very big deal. And so like this sort of things of considering the divisibility properties of the dimensions of irreps lead to incredibly deep questions, many of which are still completely open, like 60 years old. Okay, now one more thing that I want to say as a remark, which is very important, is that all of the theory that was developed thus far, with the CDE triangle, with simples, with projectives, you have bijection between simples and projectives, they projective colors and all of that. All of it works block by block. Okay, so remark, maybe I'll just say the CDE simples corresponding to projectives works block by block. So what do I mean by that? I mean, for each block, you get a CDE triangle. You get that this map is surjective, this map is injective, the matrices are transposed. Like the only, and you can still view them as Brouwer characters. The only thing which maybe you no longer have, or the thing which I'm not as sure about, is whether you can characterize the image as nicely as in the case when you do everything globally. But like, sort of all of the CDE stuff works block by block, and a general sort of paradigm in this picture is that you can work block by block rather than working with the whole group algebra. And that's very, very helpful. Or like, there are lots of things, like the group algebra is sort of all of these blocks put together, and when you restrict attention to just a single block, you can say much stronger things.
Is that hard to show? Assuming one understands CDE.
What's that?
Is that hard to show that CDE equals block by block? Assuming one understands.
No, it's not hard to show. It's go through the proofs, or your intuition for usual CDE, and notice that you only ever use the fact that there are maps between things. If there's no maps between things, sort of things break up. So the way to think about it, if you take the big CDE triangle and you arrange your projectives and your simples by the blocks that they're in, everything becomes block matrices. That's the way to see it. And because like the entries in the CDE triangle will sort of correspond to dimensions of mapping spaces. And they don't interact because that's sort of what block saying says, that they don't interact with mapping spaces. Okay. So this sort of working block by block is a really, really powerful idea. And I think it's really like, I don't know, it takes a bit of getting used to, because you no longer have a concrete description of what representations that live in the principal block look like, right? So at the start, you hear representations of the group, you say, oh, I know that category, I know what's in it. But passing to a single block actually makes your life a lot easier at the cost of not always, it's not always as clear what's actually in there. But formally, it's like breaking your thing up into smaller pieces. Is the theme that we're seeing a lot here. Okay. So, and maybe I'll say one more thing, because I think it's a very good remark, which I told Daniel last time. So in characteristic 0, it's another remark. In characteristic 0, the idempotent corresponding to a representation B is the sum of dimension B of G, character EG. So, this is in the group alpha.
Sorry, what's the symbol underneath dimension of B?
G. But order of G. Sorry, thank you. And so
What's A of A? What's the
E of E?
left-hand side?
This is the central idempotent corresponding to B. Of B. So this is like in the characteristic 0 picture, KG breaks up into products of matrix algebras. Each one of those has a distinguished idempotent. I'm going to call that EP. Yes.
Not to be confused with the A on the other side, which is the index for the like group.
Yes. Not to be so. Maybe I don't know, but like I don't want to change either. But yes, not to be confused with this.
Could you abuse notation and say that the group is contained in the group algebra and by EG is G?
You could abuse notate, yeah. So that is possibly a better way of writing as G instead of E. Great. And now I want to sort of put yourself in
Let me just comment. So you really see now why those V and whatever the ones with the maximal dimension divisor are really nice, because you kind of get rid of the poles that come from the order of G, right? So you
exactly.
cross them out.
Exactly, yeah. So like the idea is, we want to reduce this mod P, right? We've got an idempotent in our group algebra, we want to reduce that mod P. You can't do it if your dimension, like if this has some power P in the denominator. So that sort of, like if you look at this formula and think, oh, I want to reduce things mod P, you should start looking at how many powers of P divide your dimension. Because you already see that if enough of them divide the dimension, you can just reduce it immediately and you're happy. And in general, another way of describing a block, or like you want to describe the things which live in a block. So EB, so this is in A of G. So you can think of A of G as sitting inside K of G, because it's the fraction field. And then the idempotent corresponding to the block is the sum of EB for V in the block. So this is another way of restating that the characteristic P thing, has some subset of the characteristic zero things. But you can interpret this formula in a more naive way and say, okay, I've got a bunch of idempotents in this algebra. I want to be able to reduce things mod P. So I'm going to add them together until I'm allowed to, right? Like you've got poles showing up here, and you basically, you want to find a way to add these idempotents together such that you can reduce mod P. If you do this in a minimal way, that gives you the equivalence relation given by blocks. So, and that also explains why, if you had something with where the dimension of B had lots of powers of P dividing it, you could reduce it immediately. You wouldn't need to add any idempotents before you could reduce it. So this block equivalence should really be thought of as what happens when you try and reduce the character table mod P, or you try and reduce central characters. You can always reduce the central characters. Can you reduce the idempotents? No, you have to sum them to clear, sum them in some tricky way. Your denominators will clear, and you can reduce them. You're happy. Okay.
And just to comment that when you do this in practice, it seems like an utter miracle.
Yes.
You take little sums and tick, and then everything cancels. Oh my god, it really feels like it's meant to be.
Yeah. And for instance, another thing we saw last time, that the Brouwer character of projectives vanishes on elements that are not P prime, which means that if you take one of these minimal sums, you're trying to clear denominators on every element, but when you find one of these minimal sums, suddenly almost heaps of stuff is going to vanish, because the sums of these things will vanish on elements which are co-prime, which are not co-prime. So it really does feel like there's some, I don't know, miraculous numerics going on when you actually play around to try and do this.
So what would be the order of proof? Using this fact to prove this one, or the other way around?
As in to prove which one?
Say you can reduce the idempotents nicely, then your simple module lives in a block. These are kind of probably somehow equivalent statements. Which one is somehow easier?
I think I guess my interpretation is like this is sort of all taking place on the centers, and when you pull back something mod P, these different idempotents look the same, but I'm not sure. Like I think there is a nice sort of algebraic way to see it, that like these two things are exactly the same decomposition, but I think I can only have one direction clear in my head.
Yeah, to me it looks like they're probably equivalent, but I mean playing with idempotents, as Jolly just said, is a bit miraculous from time to time. So maybe the direction goes in this way. So using the numerical facts to prove the idempotents work out nicely. I don't know, I'm just asking.
Well, no, I don't think it's numerics. I think this should be a general, like, you start with a K center of this guy. Maybe I'll say, oh, okay, yeah. So like, take a central character which lives in, lands in O, some ring of integers. Reduce that mod P, except view it only on the conjugacy class sums, so your scales are valid. Then you get your central thing here, and then I think it's like the ones that you start with that give you the same things here are exactly given by this relation. And when you interpret this central character reduction mod P stuff, that's what gives you that.
Right.
So yeah, I don't think it's involves the miraculous like numerics. I think it's just an exercise that I should probably do. Okay. So yeah, so what I sort of want to give with this is that like this block stuff on one hand is quite it's like quite an abstract categorical way of breaking up the category into pieces, but you can also do it by hand. Like it's not some mystery what these things are. And like it's quite a good exercise. So maybe that, I don't know, I'm tossing up which exercise for this week, but to just like do something just for the principal block. Right? Like compute a CDE triangle just for a principal block and don't look at the other ones. Just to see that, oh, everything actually works as it should. Okay, so now I want to talk about like I don't know if I'll have enough time to give good treatment, but I want to talk about probably the most important invariant of a block. Okay, so the idea here, as Jordan was saying, is you can sort of think about these sub-algorithms like some of them are more complicated than others. The simplest ones are matrix algorithms. But then you've got more complicated things. And we already sort of, this idea that the principal block is the most complicated can be made more precise using this invariant of a block called the defect group. Okay, so so I've got two definitions of defect groups, one of which is a conceptual definition which is a bit more categorical, not as computational. And then I've got one which is the complete opposite, can be read off from the character table, very down to earth. It's not clear that these two things are equivalent. I guess I'm just asking, what would people rather hear first? Because I don't have that much time, so like, would people prefer more abstract definitions and more like, abstract theory, or, here is a group and a number associated to characters which measures how tricky the block is. Second option. Second option.
I like numbers, yeah.
Okay, great, fantastic. In that case, first off, we're not even going to have a group. We're just going to have a number, and this was originally how it was defined, I believe, and then people worked out that it could be a group. So the defect definition, the defect of a block is the largest power of P, or it might be the exponent, but I'll say it this way: largest power of P dividing some G mod dim V for V in the block, where V is characteristic 0 irregular. Okay, so this is just some number, right? Like, this is a numerical invariant of the block. We start with this block. We take 24 divided by 3 to get 8. Largest power of 3 that divides it is what is it? 0?
0, yeah.
Yeah, because it's co-prime to 3. So that tells us that it's defect 0, which justifies the terminology I used in the previous lecture. But then, you do this one.
I mean, it depends if you're saying largest power of P, or do you mean the exponent or not?
Yeah, I wasn't sure because I really like the phrase, like, is exponent the standard? Or is, like, because I like the largest power of P, because then you can say the defect equals the size of the defect group. But otherwise you need to
So
introduce
it should be
exponent.
1, not 0.
Sorry, yeah. So by this definition, then yeah, the defect is okay. Yeah. All right, yeah, good point. Is the exponent of which is a little bit, it's the exponent of the largest power of P divided this. Therefore, we can say defect 0, and that agrees with previous terminology. But you see here, this is not a new particularly important distinction. And the idea is that this is like, the way to think about it is large defect, more complicated block. Okay, like it's as a very coarse measurement. Defect 0 blocks are the easiest. The principal block has defect, the highest order, the highest power of P dividing your group order, or the exponent of that. That's going to be large. So the principal block is the most complicated.
But this definition needs some justification, right? So all of your V's in one block, like in this example, they need to be co-prime to 3, for example. Or is it
No,
obvious?
as in, so what's not obvious is that
dividing
this
sum.
is an integer. Yeah, so it's
This is sum, yeah, exactly.
Yeah.
Yes.
So like, consider all of the V's in the block, find the largest power of P dividing this number, for any of them.
Oh.
Yeah, so that's why, say, in the mod 2, we could look at this one and then see, 4
Yes.
divides 24 divided by this, but then we look at this and say, but 8 does. So it's defect is 3.
So it's really sum, not any.
Yes.
Yes.
Yeah, the any case is the height 0 case.
And so you range over like all the things about the circles.
Yeah, that's it. And like this is at the moment it's not clear at all why this. Well, maybe you could imagine that this integer sort of controls reduction mod P properties, so you can think that this is something to look at. But very important proposition.
It's obvious, but it's the worst order of pole occurring in that formula.
Yeah. Right. Okay, yeah, and that's a larger pole. Obviously worse if you want to clear denominators. Yeah. Okay, great. Okay, so there is a subgroup, or really I should say conjugacy class of. There is a subgroup D, the defect group of E with, and maybe I'll call this the D of B. So then this is D, the defect, with the order of D equals P to the defect. So at the moment, so this is to say that this, numerical description is secretly the order of some subgroup which we can associate to the block. So some conjugacy class of subgroups which we associate to the block. So, and we call this conjugacy class of subgroups the defect group. Okay, and so if this was a measurement of how complicated the block is, how complicated the defect group is a more refined measurement, because there's lots of different ways that P group can be complicated, more than just its order. Okay, so now I'm going to tell you how to find this thing. Of course, at this point, it's sort of not clear categorically what such a group does. But we'll tell you how to find this. So this is at least a definition of something that you can really work out by hand, sort of from the character table and your subgroup structure.
Chris, can you just pass? I just having trouble passing that proposition. So are there two groups appearing or one?
So yeah, so this is
Subgroup of
a subgroup DB inside G.
Oh,
Yeah, so B is a block of GD.
For all blocks, there exists a subgroup.
okay. I
Yeah.
thought it was subgroup of something called the defect group.
Yeah, no,
I just misinterpreted.
You didn't really state anything, right?
no, yeah, this is absolutely useless statement at the moment. This is just saying there is a defect group out there.
That's, yeah.
So what, right? Like, the point to take away from this is that if this is a measurement of complexity of the block, we have a more refined measurement. We can upgrade it to an actual subgroup or conjugacy class of subgroups. And so at the moment, I'll tell you what this subgroup is, but you'll have to believe me or wait a little while to see like why this actually measures the complexity of a block. So this is the definition, and this is some absolutely wild numerics. So proposition, or I guess definition in this order. Definition, DB is a P style of subgroup of the centralizer of some element G for any G with the sum be in the block of the G and the centralizer which is another way of writing central character, both non-zero mod P. Okay, so there's lots of sort of paths here, but this is saying, given a character table, given a decomposition into blocks, for any element G, this is an integer, this is an integer, or algebraic integer. If both of them are non-zero mod P, take Sylow subgroup of the centralizer of that element, that is the defect group of the block. So, and there's a lot of things that you could sort of complain about here. For instance, is this conjugacy class well defined? No, it isn't. Is it obvious that these are integers? I would also say not completely obvious, no.
No, but they're not. Like,
sorry, I was brain.
no, they're. My picture is that as you vary G, like one of them's like very divisible by P, and the other one's has a big whole order of P, and then as they line up, because that one on the left is not obviously. I mean, it's not an integer. Like plug in the trivial representation. On the left.
Sorry, the one on the left.
Yeah.
The trivial representation. Sorry, I should say it is in A though. So like it's P prime. So so the point, it's not enough to say that these they're not algebraic integers at all. Sorry, completely got that wrong. But they are potentially co-prime P, like they are in A. So I'll say that this is in A. And this thing is also in A. So it makes sense to reduce them mod P. So
But if you choose the identity, if you choose the identity.
yep.
then the first sum.
Yep.
Wouldn't that be a rational number but not be an integer?
Yes,
It's an A.
yes,
Oh,
so it's an A,
okay.
yeah, so this one's always an algebraic integer, this one is not. But the point is, like, you can reduce it mod P. In other words, this thing has no poles at P. So it's perfectly valid to reduce this mod P, and you can just ask that it's non-zero. Correct.
Is that something like the biggest subgroup where some idempotent is reducible and gives me an idempotent or something?
I think the answer to that is yes,
Okay.
but I'm not yet well versed enough to like give a better answer than that. I think for someone who is very comfortable with these and like the brow homomorphisms and stuff, I think that intuition is right, but I sort of can't yeah. I don't think I can say more than that.
Yeah. It looks a little bit like these are the coefficients in some idempotent.
Oh yeah, sorry. So this is the coefficient of G in some in the idempotent.
Yeah, and the other one.
And the other one is the like character value. Oh, sorry, the central homomorphism of the block. So it's sort of saying you want your coefficient to be non-zero, and you want your image in your your image in your character of the center to be non-zero. But like why this all works, I definitely haven't sat with. Like, to me, this is sort of numerical math. Especially because there are sort of conditions. If this is non-zero, you're either contained in or contain this thing, and if the other one is you're contained in or you contain. So like I think that's the plus or minus thing that's going on in your head. But yeah, to me, so this is sort of a definition, which at the moment is basically math. To me,
It's like quick to remind people what p-silo subgroup is.
Oh yeah, so in any finite group, for any prime P dividing the group, you have a subgroup, basically the largest P subgroup sitting inside. The largest subgroup inside whose order is a power of P. It turns out there is a unique conjugacy class of those subgroups, and you call any group in that conjugacy class a p-silo subgroup. So yeah, you want to think of it as like the biggest P group sitting inside this. Yep.
So will this be like uniquely determinate? Like if you take any group in that conjugacy class and like require these two things, that picks out a single subgroup?
Yes, but so this subgroup could change, but the silo P subgroup inside it doesn't. So yeah, so the fact that it's any G with these two properties, the fact that this pins down a group uniquely up to conjugacy isn't obvious.
But it's only up to conjugacy.
It's only up to conjugacy.
Okay.
Yeah. In this picture, sort of groups are always only up to conjugacy, or elements are only up to conjugacy.
Because we had this discussion about some and any. This is now really a proposition somehow, right?
Yeah, proposition definition, like the proposition is this makes sense. Yeah, and I mean this is sort of the price we pay for not seeing the conceptual definition first, but this is at least nice that you see that this is, this defect group of a block is something that you can compute. You really could, sit down and compute this thing. And so maybe it's worth pointing out two explicit examples. So the principal block, one can check that the identity works in both of these cases in the principal block. So what that gives you is that in the principal block, the defect is the silo P subgroup of G, or a silo P subgroup of G. So that tells you that the principal block has a large defect group, aka is conjugated. In these cases, you can check that it's trivial, right? Like, oh yeah, this is not. Okay, yeah, this is sort of surprising in these cases because, like, this tells you that certain centralizers are coprime P. So even in the case of defect 0, this is saying something surprising. Which I didn't realize before. Yeah. So in the trivial block, you can see that this thing is being complicated, but in these, it's like, if you have defect 0 characters, that's saying something about these subgroups. Saying some of your conjugacy classes don't have like p subgroups sitting inside. Okay. So, trying to go down. Not much time. All right. Does anybody have any questions about about this definition? I realize I haven't sort of told you what this is used for, other than just saying you've got to believe me that it's a measurement of how complicated the block is.
Is it possible that no such G exists? Like, is that what's going on in these cases?
Like little g.
For the principal, simple principal ones. There's no such no G. So
No, a G always exists. Yeah. So and that's like sort of a bit surprising, you'd say. So I think in these cases, this is p equals 3. So this would be saying that there is some conjugacy class whose centralizer is co-prime to 3. And in this case, I can look at this conjugacy class, and I think this conjugacy class also, maybe this one also, are all co-prime to 3. So there are a few things, but yeah, like the well-definedness of this is a bit of work. Okay, but now I want to give a conceptual way in which the defect group controls the structure of the model. So for those who like categories, this may not speak to you, so I'll try and give a definition which may speak to you. So definition, B, a G module is relatively H projective if B is a summand of IHG. So you restrict B down, you induce it back up, and if B is a summand of this, we say that it's relatively H projective. So there are also equivalent definitions. Equivalently, B is a summand of IHG U or some U. And there is also a sort of splitting condition, which is equivalent to which is like the analog of the, ordinary projectivity corresponds to certain maps always being split. There's a relative version of that, which I won't write down. So, okay. Now.
And it's not the same thing as just being projective over KH?
No, it isn't. Consider the
trivial modules projective over the CLP subgroup. Everything is relatively projective over the CLP subgroup. Yes. Everything is relatively projective over the CLP subgroup.
Yes.
So, yeah.
Yes.
Yeah, that's true.
Yeah, I would say this is a deceptively tricky definition. Like it's, you can write it down, you can say, oh, okay, I see what's going on, but like, even just proving the equivalence of these two things is not as easy as it is in the ordinary projection case. Okay, so now the important lemma is that if Q inside H is a CLP subgroup, then B is relatively H projected if and only if B is relatively Q projected. In other words, like if you go up by index which is co-prime to P, you don't change relative projectivity. Right? And the proof of this is that, like, these two things, one of them is the sum end of the other. So, in the interest of time, I won't write the proof, but the proof is not too hard and is written in notes. Okay, now I can give the conceptual definition of defect group. And so this is also, I just want to flag an important definition, which we'll probably come back to, because it's sort of the key definition for structural understanding of RepG, where structural means not doing everything semi-simply and looking at characters. So structurally, this is the key definition to sort of local representation using green correspondence, and like it's very, very important definition. So we'll almost certainly come back to it. But okay, so now I can define the defect group. Group of B is the minimal subgroup, sorry, conjugacy class of subgroup B such that all the in the block are relatively be projected. Okay, so this is sort of a much more refined way of saying that this controls the homological complexity of the block. Right? When everything is projected, your life is very easy. Everything being projected is equivalent to saying that everything is relatively E-projective, which is saying that your defect group is trivial. And so this general case is saying, okay, the bigger your defect group is, the further you are away from being semi-simple, the more homological complexity you will have in your block, and so the more complicated it is. Yeah, that's the like, so, and this is sort of, from this definition, it's not clear at all how one would compute the defect group, but we saw before you can compute it via the character table. And then it's sort of still a bit of a mystery to me why these two definitions agree. I think I'll need to sit and learn the material a bit better. But I think this definition at least should give you the impression that this group controls an enormous amount of homological structure. Yeah, and the idea of like taking a block and its defect group, that's like a very well-behaved piece that can be transported between different groups. Like the group algebra of a single group versus the group algebra of another group, hard to say, but if you take like a block and correspond to blocks and their defect groups agree. So this is sort of like a local invariant of a block, which is preserved under things that we'll see next week. Yeah, and also I believe Jordy, what was the definition, the like properly homological definition of the defect group via the derived category? Because I remember you had one, but I don't remember what it was.
Yeah, so it's the smallest subgroup such that restriction is faithful on derived categories.
Okay, fantastic. And that's probably not too hard to show from a description like this. Yeah. And so one way to like sort of emphasizing this, block by block perspective is that if you just work in KG and you want to find a group which does this, you're forced to use the whole Silo B subgroup. Like if you want to find something which is the trivial representation is relatively projected for, you have to have the whole Silo B subgroup. But if you pass the blocks, you can work with less complicated P groups inside your group, and they can sort of control your block to an extent. Yeah, so this is really to me what the defect group like does. Whereas the previous definition was okay, how do you find it? Great. Does anyone have any questions? Fantastic. It's 6 o'clock. Maybe I will just end with something which I think is worth knowing. So, or maybe sort of said this a few times, but a hell of a lot of this theory was developed by Rao back in, I don't actually remember when, it would have been like the
50s.
50s. Yeah, I mean, I guess he had a pretty long career as well.
Yeah.
And he came up with basically all of this stuff, and he came up with some incredibly influential conjectures, many of which are still open today, and now we basically have the like language to say them. So we saw before, so okay, yeah, so here is one, just because it's worth knowing. If B mod in B all have the same power of P dividing them, or B in a block, then this implies that, sorry, maybe I have a capital as conjecture, which is now an incredibly deep theorem, that the defect group of the block is abelian. So this is like, yeah, the defect group of, so this is one measurement in which, you know, these things could be well behaved, and this implies that the defect group is abelian. And yeah, this is like 6-year-old conjecture, which was proven last year. And maybe before I
That's the height 0 conjecture, right?
yes, yeah. So this is Brouwer's height 0 conjecture.
And proof uses classification of finite simple groups.
What's that?
Proof uses classification of finite simple groups.
Oh, absolutely. Yeah, like absolutely. So the other thing, this is definitely a bit of a personal rant of mine, but you have these incredibly beautiful structural conjectures, but to my knowledge, there is not yet an incredibly beautiful structural theory which answers them or says why they ought to be true. Like in some areas of mathematics, you say with the Bay conjectures, for a long time, people knew what they were looking for, even if the proofs were really, really hard and they didn't know how to prove it. They knew morally what ought to be going on to explain these incredibly deep conjectures. My impression is that that does not exist in this world. We've got the beautiful conjectures that are indicative of incredibly deep mathematics. We just don't know what the hell is going on. But, okay, and that's my personal. So I want to end with maybe one more conjecture, also due to Brouwer, which is still completely open. So if you want something to think about on the bus.
And also, many people agree with your personal rant, I would say.
Oh, excellent.
It's not like a crazy.
Okay, fantastic.
Is your personal opinion roughly saying that groups are pretty random? So maybe it's kind of hard to see.
No, my personal opinion is that like we haven't had the right idea yet.
Oh, you're actually hoping for, okay, I see.
Absolutely,
Okay,
absolutely.
okay.
I mean, you can't have all of this beautiful mathematics without having a reason for it. Like, yeah, that's I guess maybe more.
Maybe like in the next lecture, just work it out on the bus.
All right, here's another conjecture. This is called Brouwer's AB conjecture.
Oh yeah.
So this is that the number of simple irreps, so this is in characteristic 0 in block, is less than the order of the defect group. Right, so this is another sense in which one could say that the block, also the defect group controls the complexity of the block. It gives an upper bound in the number of irreps.
So if this one is still open, I would guess my question from before is also still open when I was asking about the number of simples per block.
Yeah, I mean, yeah, like it wouldn't surprise me if the
sorry, the number of simples in the principal block.
yeah, but I think the number of symbols in the principal block Yeah, okay, yeah, it's always so that would be open, given that this is.
That's what I'm just guessing right now.
Yeah, so like, this is a quantitative way in which the size of the defect group, or just the size of the defect, controls how complicated the block is in this dimension, in this like direction, right? Because there's lots of directions in which things can be complicated, and this is, you know, the conjecture about one. Okay, great, and I'll stop that.